Hello everyone. In this video we are going to learn about the full state feedback control. Now that we are familiar with different representations that we can have in the state space domain, it's time to see how this state space representation could be helpful in designing the controllers. If you remember, in the previous approaches that we had for designing the controllers in using the closed loop control scheme, we were measuring the outputs, usually measuring the output, and then we were comparing it with the reference signal, which would give us an error signal that would be used as the input to the controller. That's what we had with the root locus approaches and with the body diagram approach. But now here, in the case of full state feedback control, it will be a bit different. So what you see here in the first part of the block diagram is the state space model of the system itself. So this is indeed what we have for GP, we can say, yeah. GP of S could be represented in the state space form. We have X dot, let me write it down again here, X dot, which is equal to A times X, and we have it here, plus B times U. And we have it here. And for Y, for the output, we have C times X plus B times U, where D is equal to 0 in this case. So what you see here, and we have a feedback inside indeed the plant itself, is the state space representation of the system. Now, in order to have the full state feedback control, we will measure the states. So we have X here, they will be measured and they will be multiplied by a factor, we call it the state gain, K. With negative sign, they will be compared, or they will be added to the reference signal, and that will give us the control input or U. So what we see here indeed is the plant, yeah. So we have the plant here. K will act as the gain of the controller for us. So let's see what we will have in this case. The U signal here, U will be obtained as R minus K times X. K will be in the form of a row vector, and its size will depend on the number of the states. Yeah? So for K, we will have it as K1, K2, K3, and for X, we already have it in the form of X1, X2, X3, if we have three state variables for simplicity, and therefore U will be equal to R minus this row vector times the column vector, and this will give us a single value. So we'll get a single element here, yeah, as a result. For simplicity, for now, we will assume that R is equal to 0. Later, we will see how to deal with the cases in which R is not equal to 0. And therefore, U will be obtained as minus K times X. K is called the gain matrix for our controller. And our aim here in designing the controller using the state feedback would be to design or find proper values for K. So the main aim here would be to determine K, because this K will determine the location of the closed loop pose of the system. And we know that the location of the closed loop pose of the system will determine the behavior of the whole system. Yeah. Later we will see that designing the controller could be separated from designing the observer. That will be the topic for another video later. And in order to have the system stable, we would need to have both the controller and the observer being stable. But we will discuss about it later in the next videos. Here you can see the schematic again. We have R set to 0, so R of t is equal to 0 in this case. The U signal is equal to minus k times x, and we have the model for the system as x dot equal to ax plus u. We can also show the output signal here, y, which receives the same states, and we will get c times x. So again, our aim would be to determine the value for k. Now let's see how we can do it. X dot is equal to ax plus bu. This is what we have for our plant. That's the state space model of our plant. And our control feedback gives us u equal to minus k times x. Now we can replace u with this value. Therefore, we will get x dot equal to a times x plus b times minus kx. And that's what you see here. And as a result, we will have x dot equal to a minus b times k times x. And now we can form the characteristics equation associated with the system that we have here. The characteristics equation will give us the pose of the closed loop system. And we will get it in this form. Determinant of lambda I minus a minus b times k equal to 0. This will give us the closed loop pose of the system. For the open loop system, if we wanted to find out the pose, we would need to find determinant of lambda I minus a equal to 0. This gives us the open loop pose. Now you can see that the location of the closed loop pose of the system will depend on the value of k, or the state gain. So if we determine proper values for k, we will place the closed loop pose of the system in the desired locations. And our next step would be to determine how to pick proper values for k. But before going into that direction and determining how we find the value for k, we need to discuss about the fact that we assume that all the states of the system are measurable. Yeah, we have access to the states x, we measure them, and then we feed them back using the gain that is mentioned. If we have the pair of A and B, which are the matrices for our system, we can determine k to place all the system closed loop pose in the left half plane, and indeed wherever we want. And obviously we would want our system to be stable. But this will happen if and only if the system is completely controllable. So this is important. If you want to have a control on the location of the all closed loop pose of the system, our system should be fully controllable. And this means that the controllability matrix, PC, should be full rank. So PC is the controllability matrix. So controllability matrix should be full rank in order for us to be able to design a controller which sets the closed loop pose of the system in the desired positions. And for a SISO system, for a single input, single output system, this means that the controllability matrix is invertible. So its determinant is non-zero. We will see in examples what happens when the controllability matrix is not invertible or it is not full rank. If we consider also the effect of R, the reference signal, the closed loop system will have this form. So we would need indeed this N here, and we will discuss later why we need it. But U in this case will become minus k times x plus n times R of t. If we set R equal to 0, then we will have what's known as the regulator problem. And this means that we desire to compute k such that all the initial conditions that we have will be derived to 0 in a desirable fashion. And this will be determined by the design specifications, such as the settling time, rise time, overshoot, and so on and so forth, as we had for the other controller synthesis approaches. When we use the state variable feedback, the roots of the characteristic equation will be placed where the transient performance meets the desired response. So obviously, since we are dealing with a controller design, we will have some desired specifications. And those desired specifications will give us the desired location for the closed pose of the system. And then, having that in mind, we will have also the location of the closed pose of the system based on the state gain. And then if we equate these two, we will find values for the controller's gain. So here we have an example. A system is given in the form of, is described by a third order differential equation, as you see here. And we can obtain the steady state space model for the system as is shown here. So x1 will be equal to y indeed, the output. x2 will be x1 dot, and x3 will be x2 dot. So we have the specification for, or the representation for the system in the state space domain, as you can see here. So this is something that we have covered in the previous videos. We have the controllable canonical form. Here we have the A matrix, B, C, and D is equal to 0. And now, if we have the full state feedback, we have 3 states. Therefore, the K matrix will have 3 elements, K1, K2, and K3. It will be in the form of a row vector. And we will have U equal to minus Kx. Now, for the closed loop system, we will have the system described as x dot equal to A minus bk times x. This is something that we already know. And then we will have the state feedback matrix A minus bk having elements like this. So only the last row will change. Minus 2 minus k1, minus 3 minus k2, and minus 5 minus k3 will be the elements of the third row, and the rest of the matrix will remain the same. On the other hand, we will have a desired characteristics equation. We call it delta lambda here. So this is the desired one. Since we have 3 poles, we would like to place one of the poles far from the origin, and the other 2 will give us a response with a low overshoot and with the settling time that we would like to be equal to 1 second. So with them, we will get values for omega n and zeta. But on the other hand, for the closed loop system with the controller design there, and with the state feedback matrix here, we have the characteristics equation obtained as this expression. So lambda to the power of 3 plus the rest of the terms. We have the characteristics equation for the closed loop system. On the other hand, we form the desired characteristics equation. So by setting values for the settling time and also for the overshoot, we find values for zeta and omega n, and by replacing them, we have the desired characteristics equation. So we have the desired one. On the other hand, we have the actual one for the closed loop system. If we equate them with each other, we will have the values for K1, K2, and K3, and therefore K will be found. So K will be equal to 862, 263.4, and 28.6. If we choose these values, the closed loop pose of our system will be located at, one will be at minus 24, and the other 2 will be located according to this equation. And in this example, you see that we are able to find values for K in order to satisfy all those requirements. Here we have an example where our system is not fully controllable. in the previous case the system was controllable and we were able to find it. So in this example, we have system expressed as x dot equal to ax plus bu. We have two states, a is equal to 1, 1, 0, 2, and b is equal to 1, 0. The closed loop state feedback matrix will be equal to a minus bk, where k is equal to k1 and k2. We have two states only, and therefore the closed loop system's matrix will be obtained as 1 minus k1, 1 minus k2, 0 and 2. And if we find the determinant of this matrix, not the matrix itself, but determinant of Si minus that matrix, we will get this characteristics equation. And over here you can see that we have control only on one of the closed loop poles of the system. So we can determine the location for that, but for the second one, it will be always located at s equal to 2. Our system will remain unstable and we cannot do anything regarding that pole. Let's see why this happens. If we form the controllability matrix, as you see here, which is obtained as B and AB, B A times B, we will get the controllability matrix as 1, 1, 0, 0, and you can see that the determinant of this matrix, the controllability matrix, is equal to 0. So it is not full rank. Our system is not fully controllable, and that's why we were not able to determine or find the proper values for k in order to have the closed loop poles of the system in the desired locations. We were able only to control one of the closed loop poles, this one, and not the other one. So before designing the controller, we need to check whether our system is fully controllable or not. You need to check the controllability matrix to be full rank. When we have only few states for our system, like 2 states or 3 states, it's easy to do it manually. But when the number of states increases, it won't be easy to do it manually. In this case, we can refer to a formula which is known as Ackermans formula, and it will make it much easier to find the values for the controller gain. Let's assume that k is in this form, k1, k2 up to kn, so we have n number of states. We have u equal to minus k times x, and we have the characteristics equation in this form. Q lambda is equal to lambda to the power of n plus alpha n lambda n minus 1 to n minus 1 plus alpha n at the end. So this will be our desired characteristics equation. Once we have it, we can find the state feedback gain k in this form. A vector of zeros with a 1 at the end multiplied by the inverse of the controllability matrix multiplied by Q of A. Q of A is formed in this way. We refer to the desired characteristics equation, Q of lambda, but instead of lambda we will use A matrix. So we'll have A to the power of n plus alpha 1 A to the power of n minus 1. And finally, for the last element, alpha n is a single value, so it will be multiplied by the identity matrix I. And with this, we will obtain the value for the state feedback gain matrix, let's say, quickly. Here we have an example. The system is given in the form of a differential equation. Second derivative of y with respect to time is equal to u of t. The transfer function is equal to 1 over s squared. So we have in the two poles at the origin for the system, for the open loop system. We want to determine the feedback gain to place the closed loop poles at minus 1 plus minus I. So our desired characteristics equation will be this one. We want to place the poles here and there. Alright, so we can see that we have, for the characteristics equation, we have 1 here, 2 here, and 2 here as the coefficients. We can form the matrix equation for the system, G of S in this form. X1 dot equal will be equal to dy over dt, which is equal to x2, and x2 dot will be equal to u of t. A matrix and B matrix will be defined in this way. A will be equal to 0, 1, 0, 0, and B will be equal to 0, 1. So this is just converting the transfer function into the state space model. And once we have A and B matrices, we can form the controllability matrix. It will be equal to B and AB. So depending on the number of the states, this could eventually increase. If we have 3, 4, we will have B, AB, A squared, B, A to the power of 3B, and so on and so forth. But when we have only 2 states, this will give us the controllability matrix. We have the controllability matrix, then K will be obtained as using the Ackermans formula in this way. So we have a vector of zeros with a 1 at the end, multiplied by the controllability matrix inverted, multiplied by Q of A. For Q of A, we have it here. A squared plus 2A plus 2 times the identity matrix. A squared plus 2 times A plus 2 times the identity matrix, and we have it here. For the controllability matrix, we need to find its inverse, so we have it here. And then if we plug all these into the Ackermans formula, we will get K equal to 2 and 2. So with these values for K, we will place the closed loop pose of the system at -1 plus minus J. Note that in finding the state gain using the Ackermans formula, we are referring to PC inverse. So the controllability matrix should be invertible. In other terms, it should be full rank. If it's not the case, we will not be able to find the values. You can also use the MATLAB commands in order to apply the Ackermans formula using the Acker or the place commands of the MATLAB, where you provide A and B and the desired location for the pose. So this is indeed the desired closed loop pole locations. You don't give it in the form of a polynomial, but you just determine the location for each one of the poles of the system. And I hope you see that using the Ackermans formula, it is kind of easy to determine the state feedback gain values. Alright, so I think that's all for this video. Thank you for watching. I hope you have learned the basics of the state space control, the full state feedback in it, and how you can determine the state feedback gain either manually or using the Ackermans formula. Keep in mind that the system should be controllable. It should be fully controllable in order to perform this. And the difference between the state feedback control and the other approaches that we already know should be also clear here. So with the state feedback control, we determine the exact location for all the closed loop poles of the system. While with the other approaches, we usually don't have this option. Okay, so again, thank you for watching and see you in the next video later.